When you learn a new class of functions, you're invariably going to need to eventually solve equations involving those functions. So, now the lesson on exponential and logarithmic equations. There are two approaches you can take when you're solving equations involving exponents and logarithms. There's the one-to-one properties that you can use, which make for a pretty easy solving process. But then there's the more frequently used cancellation properties. Let me first go over using the one-to-one properties in solving exponential and log equations. What it means for to use these one-to-one properties, a function is one-to-one means that if the outputs are the same, that implies the inputs are the same. If f of x equals f of a, that implies x equals a. That's a unique property to a one-to-one function. The logarithm and exponential functions are one-to-one. So if you have an equation that says 2 to the x equals 2 to the 12th, then that implies directly that x has to equal 12. So the equation is solved. You're really solving it by this implication. Since the bases are the same and these two parts are equal, then the exponents have to be the same. So it's really an implication that you use to solve the equation. So some examples of using the one-to-one properties to solve exponentials. If you're blessed enough to have an equation that looks like this, both sides are base 5. The left-hand side says 5 raised to the 3x plus 2 equals 5 raised to the x minus 4. Well, if the bases are the same, then the one-to-one property implies, and again, that's what that double thick arrow means. Whenever you see me draw that, that's what implies means. This equation implies you can equate the exponents. So you have a 3x plus 2 directly equals x minus 7, and then you just solve the linear equation that results from this implication. Get the x's on one side, so subtract your x from 3x. You get 2x on the left. Subtract 2 from both sides. That gives you equals 9. So this equation is true if x equals negative 9 halves. And that's the solution to the equation. Okay. Now in some cases there might be a little more rewriting involved in order to get to use the one-to-one properties. You've got to get both sides written as powers of the same base. So see, this one was ideally suited for that, just like this little example up here. You can rewrite both sides of this equation as powers of the same base. The left-hand side is already a power of 10. 10 raised to the x squared plus 4x. The right-hand side can also be written as a power of 10. That reciprocal power of 10, 1 over 1,000, is 10 to the negative 3. So as soon as you can get both sides written as powers of the same base, that implies, since this is a one-to-one function, the exponential function base 10, that you can just equate the exponents. And so in this case, the resulting equation is quadratic. X squared plus 4x equals negative 3. So this one is probably best solved by factoring. Add 3 to the left. Factor out, we'll factor using the trial and error. X plus 3 times x plus 1. So you get two solutions. X equals negative 3 and x equals negative 1. So notice in making this implication, I'm not dividing both sides of the equation by 10. You're not using division here. You're just using something that has to be true if both sides are written as powers of the same base. 10 to a equals 10 to b implies that a has to equal b. So you're doing mathematics, it's just not, you're not really doing arithmetic. You're making an implication based on this statement being true. So on this one, your left-hand side is base 27, your right-hand side is base 81. So you can rewrite both of these as powers of 3. See, 27 can be written as 3 to the third. But notice, you still have this exponent of 4x minus 1 on the outside. 81 can be rewritten as 3 to the fourth. And you still have an exponent of 2x on the outside of it. So all I'm doing is just taking advantage of rewriting those bases as powers of a common base 3. And then when I use the properties of exponents, raising a power to a power makes me multiply those. So that becomes 3 to the 12x minus 3 equals 3 to the 8x. So since I can eventually get both sides written as powers of the same base, the one-to-one property tells me that I can imply the exponents are equal to each other. 12x minus 3 equals 8x. Solve this equation for x. Subtract your 8x from 12x. Add the 3 to the right-hand side. Divide both sides by 4. So the solution to this equation is x equals 3/4. So, you'll have a few problems in the homework where you can do this. You can't solve all exponential equations this way. That's why I need to show you the cancellation properties. But since we're on the topic of one-to-one, let me show you that it also holds true for logarithms. If you have log base a of x equals log base a of b, if your arguments are different but the log bases are the same, if you get both sides written as common logarithms or the same logarithms of different quantities, this implies that their arguments have to equal each other. So here the equation starts off as natural log of x plus 13 minus natural log 4 equals natural log of 3x minus 5. In order for me to get both sides in the form of ln of a quantity equals ln of a quantity, I need to do some condensing on the left-hand side first. So use law of logarithm number 2. That's a difference of two logarithms. I can condense this to natural log of x plus 13 divided by 4, and then keep the right-hand side as natural log of 3x minus 5. And now I do have a situation where I can use the one-to-one implication. Both sides are the same logarithm, and if it's condensed to where you have one logarithm equals the same logarithm, you can equate the arguments inside. So this implies that x plus 13 over 4 equals 3x minus 5. So it's a linear equation again. I'm going to cross multiply the 4 first. X plus 13. That 4 cross multiplies to give me 12x minus 20. And then solve this for x. If I subtract x from 12x, that gives me 11x. If I add 20 over here, that gives me 33. So when I divide both sides by 11, I get x equals 3. Okay. And so since that implication gives me this equation, this has to be true for the original equation as well. All right. So the one-to-one properties are handy. They're just solving by using an implication. As long as you can either get both sides written as powers of the same base, like we did on these first 3 examples for exponentials, or if you get both sides as single logarithms, you can equate their arguments like this. All right. But again, it has to be the exact same logarithm on both sides, just like it has to be the exact same base up here. So now let me go ahead and start showing you the way to use the cancellation properties to solve exponential and logarithmic equations. That's our next video.